In this problem, we're going to look at how to solve the equation of motion for a harmonic oscillator using the Lagrangian. In a moment, we'll do the same problem using the Hamiltonian. To start this problem, we first need to find what our Lagrangian is. T is our kinetic energy, V is our potential energy. So our Lagrangian becomes 1/2 the mass velocity squared. Notice I write velocity as x dot. X dot is the time derivative of x. In other words, it is velocity. But it's much easier to write x dot for reasons that will become apparent as we go along. So this is our kinetic energy, and our potential energy will come from the energy of the spring. We'll write that as 1/2 k x squared. Now, in order to solve this, we next plug it into Lagrange's equation. Fortunately, we only have one variable and one generalized coordinate in this problem, just x. So we take the partial derivative of x dot. That means we ignore x. It means we get the time derivative of the partial derivative of L with respect to x dot. We get mx dot minus the derivative of Lagrangian with respect to partial derivative with respect to x. So that means we ignore this one. We only pay attention to this one. So because this does not have an x, only has an x dot. The partial derivative with this respect to x is negative kx. All this equals 0. Now, I simplify this and I get mx dot double dot plus kx equals 0. Or if I write it differently, x double dot equals negative k over mx. Now, this equation has the elementary solution. X equals a, just some constant. Cosine, we could have just as easily used sine, does not matter. Square root k over m time. We can throw in a phase factor if you really want. That'll usually just be 0 for convenience. And there's our equation, because that's the only solution to this second order equation. We'll do this problem again with the Hamiltonian. In which ways it's an easier problem.